Yes, and today we are going to start with a new topic that is part of the unit 3, shear and bond. We have completed the part of shear. Now we are going to look at bond. Now bond, as we understand, is something which keeps two materials, two people close together. Their interaction is very close. Okay, so that is what we call as bond. So what is this bond in RCC? In the reinforced cement concrete, what is bond? What role does it play? Okay, that we are going to understand in this part of this chapter, the chapter 3, shear and bond. Now, it's a well-known fact that external load, whatever load which is applied on a beam or a column or a slab or footing, it's never directly applied on the steel. Okay, in any structural member, it is never directly applied on the steel, it is applied on the member. Or we understand that the load comes on the slab. From the slab it goes onto the beam, from the beam it goes to the column and to the foundation and further on. Now even on the slab, the load is directly not applied on the steel, but the load is applied on the top of the slab, sometimes at the side, okay, in case it is wind load or things like that, but it is always on the concrete side. It never is directly applied on the structural steel, that is the reinforcing steel in the structural member. That means the reinforcing steel which is present in the slab or the beam or the column and the footing, whatever, any member which we consider, it takes its share of the load. It only shares the load from the surrounding concrete. So that means from the concrete only it has to take the load, and then only it can share it. So over here, one important thing which we note is the steel takes the load only from the concrete, or only the concrete gives the load to the steel. So it is going to be sharing. The steel gives the load to concrete and concrete gives the load to steel. Now how does this happen? Now this transfer of load from one to another occurs due to the phenomenon called as bond stress. Now this bond stress, also like shear, is a bit complex. Okay, in understanding it is a bit complex. So most of the times we will be finding that the experimental bases are used, the assumptions are used in order to come out with the theories as far as the bond stress is concerned. What is bond? How does the bond actually take part? All this is done through the experimental work, and the things have been presented. Now the bond in reinforced cement concrete, RCC, the term is used to define, to show or to depict the interaction between the reinforcing steel and the surrounding concrete, which permits the transfer of stress from steel to concrete or concrete to steel, as the case may be. Now one thing which we have to understand over here is that yes, the transfer of stress from steel to concrete occurs, or concrete to steel occurs, but this occurs when there is strain compatibility. Now this strain compatibility means at that particular point where the reinforcing steel is present, where the reinforcing steel has been provided, where it has concrete surrounding it, the strain in steel will be equal to the strain in concrete. This is the most important part which we have to understand. The strain in steel has to be equal to the strain in concrete. Only then the stress transfer can occur. So the bond between reinforcing steel and the concrete ensures that strain compatibility exists. That is, the strain at any point in the steel is equal to that in the adjoining concrete. Next to it, whatever concrete is there at the same level, that concrete. Now it is because of bond that there exists a composite action of concrete and steel. That means it is only because of bond that concrete and steel act together, and we have something called as reinforced cement concrete. A very important term for all the structural engineers who are designing the structures. Bond is the most important thing, because if bond does not exist, the compatibility is not there, the strain compatibility is not there, the composite action is not there of concrete and steel, and if the composite action is not there, we don't have something called as RCC, and we don't have our structures. So in order to have our structures, We need that composite action, we need that strain compatibility, and finally what we need is the bond. Now why am I talking of bond so much is that this bond is not only important for structural designers who are designing the RCC members, but it is also very important to be understood by the site engineers who will be working at the site. In order to ensure this bond, what all precautions have to be taken, what are the factors which affect this bond, have to be clearly understood by the structural engineer who is designing the structure, as well as the one who is constructing it, the site engineer. So both the members need to understand this bond thoroughly, the factors, the mechanism, all this part has to be understood thoroughly by both the parties. Then only we can expect the composite action of concrete and steel to be proper, to be adequate, and the structure to be standing with more durability. Now good bond ensures that there is no slipping of steel, that is steel reinforcement, with respect to the surrounding concrete under the load. Now why this is important? This is important because we don't want the bars to slip. The bars have been embedded in concrete. The bar has been put over there as reinforcement, but whenever we are putting the bars on the formwork, there is grease which is applied. Now if these grease comes on the bar, even by mistake because of walking of the persons, or maybe while painting the thing has been done wrongly, or maybe the bars were kept down on the formwork and the bars have been lifted, so the bars have got coated with grease or oil. So in that case slipping can occur, bond will not be there. If there is no bond, we have understood that the composite action could be affected. So good bond ensures that there is no slipping of the steel reinforcement relative to the surrounding concrete under the load. A proper bond is responsible for the anchorage of reinforcement. The reinforcement remains in place because of proper bond. And the most important thing for me is the basic assumption in limit state of collapse flexure which we use. Plane sections before bending remain plane after bending also. This remains valid only if there is a perfect bond between concrete and steel reinforcement. Now why am I stressing on this? We all know that the RCC members are not homogeneous. They are not having the same properties right from top to down. They are made of different materials. Now if this RCC member has to be, acting as one, plane sections before bending has to remain plane after bending also. That means steel also has to remain in position at any point of time. So the basic assumption in RCC remains valid only if good bond is existing. Now the bond in RCC members is accomplished by the following three mechanisms. One is chemical adhesion. Now what is this chemical adhesion? Now whenever we have concreting being done, we have cement which when added with water changes into cement paste. Now this cement paste forms a gum-like material. Now this gum-like material binds all the other ingredients like sand, aggregate and reinforcement. It binds everything. Now this binder, this paste, this gum-like property in the concrete which is due to cement, okay, this is formed during the hydration. Now this creates that adhesion. This creates the adhesion between the reinforcing bar and the concrete. Now this creates bond. This is one of the mechanism through which bond acts. Now second action is frictional resistance. We all know that if good compaction is done, then the sand gets compacted, sand gets filled up within the spaces of the aggregates, the spaces in between the sand is filled by the cement, and all these remain so compact and they form a tight compact area around the reinforcing bar. Now this area, this space which is tight and compact, don't allow the bar to move out. due to the property of friction. So even due to loading, if the bar tends to move out, if the bar tries to bend and slip out, the friction created by these materials like sand, cement, aggregate, all that joined together forming concrete, that friction created together creates resistance along with the surface roughness of the reinforcing bars. The reinforcing bars have its own surface roughness and this does not allow the bar to slip. So this also is a mechanism of bond. The third thing is, if we are not using the plain bars, if we are using the deformed bars which are having ribs or deformations or protrusions, the HYSD bars which you have seen, now these create the barriers. These are like the speed breakers on the road. They don't allow the free movement, they don't allow the slipping. Okay, so these projections across the movement, across the axis of the bar, prevents the bar from moving. So now these three actions, the chemical adhesion, the frictional resistance and mechanical interlock, actually prevent the bar from slipping. Now each of these above components like chemical adhesion, frictional resistance and mechanical interlock will be working in varying dimensions, varying amounts in order to resist the slipping movement. Now normally when we start loading a particular structure, reinforced concrete member, right in the beginning we know that the chemical adhesion is there, it is holding the bar, but this chemical adhesion could be lost due to a small slip. Even if there is a good amount of load and that creates a small slip in the bar, we all know that this chemical adhesion can break, this chemical adhesion can fail. So the first mechanism could be lost due to a small slip. Now the frictional resistance, as I said, it depends upon the surface roughness and the grip provided by the materials of the concrete. The plain bars per se by themselves do not provide any mechanical interlock, but the ribbed bars provide this. Many experiments have shown that the bond in concrete is highly dependent on the amount of rib area. So it is much better that there are ribs provided over there. So if ribs are provided, they can take care of the bond easily. Now let us understand this mechanism of bond in reality. Assume that an RCC beam is constructed using plain round MS bars, mild steel bars, which are greased or lubricated, and this bar is used in construction. For a beam member, these bars have been used. Now these beams so constructed with the greased reinforcement, when it is loaded, the reinforcement will start slipping. Can you see this? The bar from here to here, which has been used, slips. Can you notice? It has slipped at both its ends. The beam has bent, the bar also has bent, but it has not bent along with the beam from the ends. The bar has bent but at a different location. So one can understand that there is loose contact between this bar and the concrete. Therefore, this type of a beam would collapse because the bar would get pulled inwards and the beam will not get that enough load transfer from reinforcement to the concrete, and then this beam would collapse. The load transfer, as we have said earlier, the strain compatibility will not be there, the stress transfer from steel to concrete will not be there, the composite action will not be there, the bars are getting pulled out easily, and hence the beam would fail. Now the experiments have been done, and therefore, in order to prevent such a collapse due to pull out of the bar, if even the greased bars had to be anchored at the ends by end anchorages, it was decided that it would be better. So the same bar, if you just observe, the same bar has been provided with end anchorages over here. End anchorages by means of hooks. They have been provided with hooks. Now such an arrangement by which we are providing end anchorages or tied or this tying over here Such an arrangement of end anchorages creates a tide arch effect. Tide arch effect. There is an arch over here which is tied at the bottom. The tide arch effect with the uncorrect concrete forming the arch and the reinforcement forming the tie. Can you see this? Uncorrect forming the arch and the reinforcement forming the tie. So the tie bar of the reinforcement has no bond stress over entire its length, and it is subjected to only tensile stress, that is flexural stress due to external acting bending moment. Now this bar is subjected to only flexural stress. There is no bond stress, so whatever bending moment is there, it is being taken care of by this reinforcement by that lever arm into its whatever force it is taking. That force in tension multiplied by lever arm would be equal to bending moment, which we have already seen in the previous chapter. So this reinforcement down is actually loaded only due to the flexure coming on it, only due to the bending moment coming on it, and there is no bond stress existing in this bar anywhere in this bar over entire its length. As a result of this, total steel elongation, this, now as we have seen, this bar is subject to the bending moment which is coming on it. The force coming on this is due to the bending moment, that is the force multiplied by the lever arm comes to equal to bending moment, external acting bending moment. Now as a result of this, the total steel elongation of this in such a case would be much larger than actual elongation of the beam bonded with reinforcement. Now due to so much of force coming on this, the actual elongation of this bar would be much larger than the elongation of this beam. What would happen as a result of this? As a result of this great amount of elongation would give rise to greater crack widths and deflections. Because there is a greater elongation, there would be greater crack width, there would be greater deflection. Therefore, the IS code prescribes the use of deformed bars. IS code talks of use of deformed bars and permits increased bond or increased bond stress in the reinforcement with concrete, thereby reducing the crack widths and deflection. So if we refer to IS code clause 26.2.1.1 page 43, we find that the bond stress which has been given is increased by 60% whenever one uses deformed bars. Now why does this get increased by 60%? It is because the bond is improved, the bond is better with the deformed bars with the ribbed areas. Now due to this, the use of end anchorages, because the bond is increased, that means the bond is better between the reinforcement and concrete. That's why many a times structural engineers don't provide hooks at the ends. End anchorages are dispensed with. Structural engineers feel that there is no need of the end hooks and anchorages whenever ribbed bars are provided. Now what is flexural bond? Flexural bond, that is the bond which we are talking about. Flexural bond can be defined as the bond which gets developed in the flexural members on account of shear or a variation in bending moment, which in turn causes a variation in axial tension along the length of the reinforcing bar. So that is exactly what it talks about. The forces in the steel members are like this, and the external forces are going outwards. So the forces are acting together, and that is exactly what is bond. Now because of this, the whole member behaves like RCC member. Eventually what we find is that the steel and concrete behaves together because of good bond. So evidently flexural bond is critical at the points where shear is significant. Where we have good amount of shear, we find that flexural bond becomes more critical. It has been observed that wherever local peak bond stresses are high, the longitudinal splitting cracks are initiated. At the point where local peak bond stresses are high, splitting cracks are starting over there. Tests on beams have shown that at the locations where the local peak bond stresses are high, the longitudinal splitting cracks tend to get started. Also, another thing to be noted, the beams with larger diameter of reinforcing bars are vulnerable to splitting or local slip. If there are beams with larger diameters of reinforcing bars, they are vulnerable. They can be easily subjected to splitting or slipping. Another observation is that the flexural cracks are generally not seen in the compression zone. Very important observation which has been found from the experiments. In the compression zone, there are hardly any flexural cracks noticed because of bonding. Therefore, it is concluded that the flexural bond is less critical in compression bars as compared to tension bars with similar force. So, the flexural bond is less critical in compression rather than tension. The IS code takes cognizance of that and permits increase of bond stress in compression zone by 25% as compared to tensile. 25% increase is permitted as far as compression zone is concerned. Now this was all about the flexural bond or the local bond. Now there is something called as Anchorage bond or development bond. Now what is this Anchorage bond? The bond developed near the extreme ends or the points of reinforcement cutoff where the reinforcement is no longer required. Wherever the reinforcement is subject to tension or compression is called as Anchorage or development bond. So when we are designing a beam at the midspan for a simply supported beam, at the midspan the bending moment is maximum. Now as we move towards the support, the bending moment goes on reducing. Obviously the reinforcement also required would be less. So one can go on cutting the reinforcement. So at that particular point where the reinforcement is cut off or at the point of the support, okay, the anchorage which is required for the bar is called as the Anchorage bond or the development bond. Now in order to understand this concept of Anchorage bond or development bond, let us consider a cantilever beam which has been shown over here, a cantilever beam subjected to some load, okay, and it is having a support on its left hand side. Obviously when we look at this cantilever beam, we understand that for this cantilever beam the maximum bending moment is at the support at this particular point, and obviously the reinforcement required is over here. Now if I move slightly inwards, from the support, if I move slightly inwards, obviously my bending moment is 0. My bending moment is maximum up to this particular point. Further on there is reaction coming up from the support. So bending moment anywhere further than this support, within the support, bending moment is 0. And we understand that when the bending moment is 0, there is no reinforcement required over there, like this. What I'm talking about, the bending moment further than this point is 0, and that means the reinforcement requirement, the design requirement of reinforcement beyond this point, because there is no bending moment, is 0. I don't need any reinforcement over there. Well, if there is a beam like this which is constructed with a support over here and the beam over here with the reinforcement up to this, do you think the beam will remain if we provide the reinforcement only like this? And if this is loaded, obviously we understand that if the bars were to stop at the face of the support, the beam would collapse, the beam would get cracked over here and the beam would get collapsed, the beam would fail. Now what we understand is that by ending the bars over here, it is not enough. The bars need to be taken inside the support. Now the bars have to be taken inside the support, and whatever force is coming over here, which is actually responsible for cracking and cutting and collapse of this beam, that force has to be transferred inside into the support. Now this force has to be transferred inside the support by the phenomenon of bond. Now this bond exists between the reinforcing steel and the concrete, and with this bond only we can transfer the pull which is there over here in the supporting member. Here the bar must extend to a distance beyond the support or within the support to develop full yield strength so that sufficient bond resistance is mobilized. So this length, the length required over here, can be defined as development length, the length to be developed, or the anchorage length, the length required to anchor the bar. So the development length can be defined as the minimum length of embedment of bars that is necessary to permit them to be stressed beyond their yield point or up to their yield point, so that when they are stressed up to the yield point, the beam will remain over there in place and it will not fail. So the development length can be defined as the minimum length of embedment of bars that is necessary to permit them to be stressed up to their yield point. So this is the bar. Please note, this is the bar which was put. Now that much bar length was not enough, so we need to turn the bar and take it within the support. We are turning the bar and taking it within the support. The supporting member is in compression, there is no problem. It will take this pull. So whatever pull is there over here which is actually trying to pull the bar out, that pull gets transferred in this and it gets transferred over this entire length. So the beam gets anchored to this support, the beam gets anchored to this column, and it will not fail. So this length over here, this length LD, which has been defined in the picture, this length over here is the development length or the anchorage length. Now how do we find out how much is this LD? We have said that it is this length as LD. By this much length we should take it inside, but how much it is? How do I quantify it? Now there is a term bond stress. The term bond stress is observed. The bond stress is observed to be varying over the length of embedment. Now if you look at this particular thing, a small segment which I have taken of a beam, okay, there is a bar which is getting pulled out, so obviously over throughout its length there is bond stress developed. This bond stress, when it fails, the bar gets slipped out. So this is the bond stress developed. Now we also know that from experimental records, we know that this bond stress does not remain uniform from here to here. Throughout the overall length it does not remain uniform. Also we find that it becomes zero at a particular point, and further length of embedment is useless because that does not take part, that particular part of length does not take a part in anchoring of the bar. So there is a definite length LD which is necessary, beyond which the bond stress is zero. Now how do we find it? Now bond length, as the bond stress is observed to be varying over a length of embedment. It is maximum at the face, and zero at a certain level, a certain distance LD. It is generally assumed that an average uniform bond stress tau BD acts along the length of embedment. So for our calculations we are going to consider that there is a average stress acting over the bar, that is average bond stress, called as tau BD. Now as per the equilibrium condition, whatever is the force of pull over here should be equal to the force of resistance. The force of pull outside is area of the bar multiplied by the stress in the bar. The stress in the bar is sigma s, area of the bar is AB. Now that is resisted by this, it is resisted by the skin or the perimeter or the surface of the bars. So that is the stress multiplied by the perimeter over the length LD. So we have stress multiplied by pi into the diameter of the bar, into LD. Having got this, the AB is the area of the bar and area is equal to pi into diameter square upon 4. Then sigma s is the stress in the bar, phi is the diameter of the bar, tau BD is the anchorage bond stress average one which we are taking over here, and LD is the development length. Therefore when we solve this, pi and pi gets cancelled, the phi and phi gets cancelled, and finally we get tau BD equal to sigma s phi divided by 4 LD. A very important relation. So when we rearrange, we get LD equal to sigma s phi upon 4 tau BD. So we now know the length of LD over here. Now the length of LD is equal to sigma s, that is the stress in this bar, multiplied by the diameter of this bar divided by 4 times the bond stress. So having known the parameters such as the stress, the yield stress or the service stress, whatever is existing in the bar or whatever would be permitted maximum, the diameter of the bar provided and the bond stress, we can easily calculate the value of LD, the development length to be provided. So the calculation is this. Now let us see what does the code say. The development length of the bars or the length of embedment is given by IS 456 also in its clause 26.2.1 on page number 42. It says LD is equal to phi into sigma s upon 4 tau BD. So it is exactly the same formula which we have got now from the derivation. So LD is phi, that is the nominal diameter of the bar, sigma s, the stress in the bar at the section considered for a design, tau BD is the design bond stress. Okay, now this development length also includes the Anchorage values of hooks, whatever, in tension reinforcement. Please note it is only in tension reinforcement, not in compression reinforcement. And it also says that if at all we are using bars other than circular, then we should develop sufficient length for the bond. Okay, so all this part has to be taken care of as far as bond is concerned. So today in this particular session, what we have understood is the mechanism of bond, how the bond acts, and what actually we need to do in order to take care of this bond. So that has been understood in this particular unit today.